Thank you, folks, for coming. My name is Jagain Sundar. I'm CTO of Vandisco, and I have Brett Rudenstein, Senior Product Manager. We're going to talk about applying Paxos to make critical Hadoop services continuously available. Vandisco, a little bit of background on us. Vandisco stands for Wide Area Network Distributed Computing. And as we go through this presentation, you'll begin to understand why that name makes a lot of sense. We make enterprise-ready, high-availability software for globally distributed organizations to meet today's data challenges of secure storage, scalability, and availability. In short, we make replicated services that are continuously available and can run in different data centers across the world. We're a leader in software tools for developers. We have SVN multi-site, Git, replicated repositories in different parts of the world. We are a sponsor of the Apache Software Foundation. We had a huge and successful IPO on the London Stock Exchange in 2012. Our patented active-active replication technology is an extension of Paxos that works over the wide area network, and that's the core intellectual property we use for all of our products. We're a globally distributed organization like most companies these days. It's a colorful slide of all of our customers. We're hoping we can grow this dramatically in the next few years. So let me start with a recap of how server software architecture has evolved over the last 15 years or so. This is relevant. Back in the days of Unix, this is prior to Linux, you had a single process, single threaded server that basically operated like this. You'd pick up a request from a client, for example, a HBase put, and you'd make a change to the state. That could be a database, it could be persistent storage on disk, and you'd send the return value to the client. Things were very simple, but as you can imagine, this was not the most scalable solution. We moved on to multi-threaded servers where you have a single process, but multiple threads operating in that process. Here I have thread 1, 2, and 3. Each of those is reading from requests from socket connections, perhaps. There's a green operation, an orange operation, a red operation, and a gray operation. But when they need to make changes to the database or to persistent state, you can't have them interfering with each other. So what you had was a need for a mutex. You took a mutex, which basically meant only one thread can operate on that persistent store. You wrote the operation out, and then you released the mutex. The effect of this was that you had a number of threads operating in parallel for the most part. During those critical operations, they operated in single-threaded mode. You got much more scalability from this, and you were able to process many more requests per second as a result of this. Of course, the problem remains that if such a process were to die or if the server were to reboot, you would lose functionality for that period of time. How can we improve on this? We're talking about having multiple replicated servers that have exactly the same data and are able to provide both read and write, read or modify operations to that particular state machine at any given time. This is strong consistency replication. There's no eventual consistency model here. If we could put such a system together, you would have no availability concerns. One server could go down, the other two would continue to service clients, and your services would be completely up and available. We can define this problem as how do you ensure that the three servers have exactly the same data? How do you achieve strong, consistent replication? There are two parts to this solution. There is something called a deterministic state machine, multiple replicas of these on each machine, and a sequence of operations or changes to the state machine that you perform in exactly the same sequence in each of these deterministic state machines. I'll go into a little bit more detail about what a deterministic state machine is so you can understand how we get these perfect replicas. A deterministic state machine is one where a specific operation will always result in the same deterministic state. Non-deterministic factors don't play a role in the state change. Examples of non-deterministic state could be time, if you call random, Time runs somewhat different in all of these nodes, so you'd get a different number, and the resultant state would be different on the 3 replicas. You don't have a deterministic state machine at that point. If you picked random and did that, the whole idea of deterministic is not valid anymore. So to go back and look at our picture, you have 3 replicated servers which have deterministic state machines in them, and we're applying the same 4 operations, the red, green, orange, and gray operations in the same sequence. And because of the definitions we've just made, you know that the end result will be 3 servers with exactly the same state, each of which can service reads or writes. So now the problem becomes, how do you reach consensus between these servers as to the sequence of operations that you want to perform? How do all of these servers apply exactly the same sequence of operations? The answer to that problem turns out to be Paxos. This is an algorithm for reaching consensus in a network of what's known as unreliable processors. These are processes or networks or systems that may stop, that may come back, and have various unreliable characteristics. In the midst of all this mayhem, we have developed an algorithm for reaching consensus. By we, I actually mean Leslie Lamport, the gentleman who works for Microsoft, who wrote this paper, seminal paper on Paxos decades ago. We go back to our picture now. We have clients connected to 3 replicated servers. I've introduced a black box in the middle called the distributed coordination engine that's responsible for implementing the Paxos algorithm and feeding the deterministic state machine with these 4 operations in exactly the same sequence. The end result is a multiple active service that can remain continuously available. Let's take a brief look at Paxos before we move on, because this is germane to our discussion here. As I mentioned, it's an algorithm for building replicated servers with strong consistency. It consists of 2 parts. There's the synode algorithm for achieving consensus among a network of unreliable processes, and the application of this consensus to the task of replicating deterministic state machines. So in reality, Paxos is more than an algorithm for reaching consensus. It's a new way of building servers. This is why I started off my presentation talking about how single process services went to becoming multi-threaded services. The next step is a natural evolution of having multiple replicated servers that use Paxos to coordinate the operations that are performed on these services, so you can get exactly the same data in all of these 3 services. As a side note, Paxos doesn't really specify a network protocol. It's not really a protocol. There are implementations that use RPC. There are implementations that just send serialized Java objects. It's left to you. It doesn't invent a new language. Thankfully, it didn't add to the proliferation of useless languages. It doesn't restrict you to use in one language or the other. You can implement it in pretty much any language you want. So the replicated state machine is installed on each node that participates in the distributed system. I'll show you 2 examples. One is the HDFS name node. There are going to be 3 of these name nodes. We're calling them consensus node, and they will participate in this quorum. All nodes function as peers, and the same transaction order, as I mentioned, is going to be applied to all of these nodes, so you end up with the same state in memory and in the edits log of these name nodes. This way, we can achieve consistent replication. To achieve consensus, Paxos defines several roles. We'll go into a little bit more depth on these roles in the next slide. The roles are proposers, acceptors, and learners. In the simplest implementation, all 3 roles will be satisfied by each server in this replica group. Again, the algorithm goes through 2 phases. There's an election of a node to be a proposer. That's phase 1. Proposal is broadcast to all peers, and the proposal is accepted as the next change in the state. And if a proposer doesn't win that round, it can make a proposal for a subsequent round. So every state machine gets the same sequence of operations performed on it. Let's take a look at the roles as defined by Paxos. A proposer is really a client or a proxy for a client. In the case of the name node, the consensus node that we're going to talk about later in this presentation, the name node that the client talks to makes the proposal. So it's really a proxy for the client in that case. It proposes a change to the deterministic state machine. An acceptor is really the memory of Paxos. This is where the set of state changes is recorded and cannot be forgotten. Quorum, majority quorum in the most useful case, is established amongst these acceptors. The learner, of course, is the action where the DSM has these changes applied to it in the same sequence. So in brief, ordering is achieved by proposers issuing a new sequence number of higher value from the last sequence known. A majority agree that this number is not being seen, and then consensus is reached on that current proposal. I want to spend a few slides explaining the enhancements we've made to Paxos. This is relevant in many regards because Paxos by itself is a mathematical proof of a new way of writing servers, but to make it useful, a lot of additional functionality needs to be added. We have many quorum configurations. There's the majority quorum, which is the most useful one. There's singleton. There's also unanimous quorum. We have the notion of a distinguished node, which has the ability to break ties between, say, a 3-node on one data center and a 3-node in another data center quorum. We have the ability to do quorum rotations without shutting down the state machine, wherein you can go and move the majority from the US during US daylight to Asia when it's daylight in Asia. There's a notion of emergency reconfigure, which is essential for normal operation of the system. We also have the ability to process multiple agreements in the state machine change concurrently. This is critical for high throughput in a system like Paxos. The groups can be evolved dynamically. This is important because if you want to go from a 3-node system to a 5-node system, you don't need to bring the system down. You can take nodes out, send it off for service, bring it back, and add it to the quorum, and functions like that. There's the notion of distributed garbage collection. The thing about Paxos is that it's more than just a network protocol or an algorithm. It has the need to persistently store certain data. During the operation of Paxos, an acceptor can't renege on some commitment that it has made to the rest of the nodes in the quorum. That means it has to be saved persistently. In case it reboots and comes back, it can't go back on that commitment that it made. That's the reason why Paxos is so complicated. It's more than networking. It's storage involved as well. That naturally brings up the question of how long do you store these agreements? How do you garbage collect those? What about the ones in memory versus ones in disk? For a normal operational Paxos implementation, you need to be able to do distributed garbage collection, which in this case turns out to be removing from memory and disk the agreements that all the members of the quorum know about. Back-off and collision avoidance needs to be done in a careful and planned manner. Otherwise, you can have a system that doesn't make progress. Self-healing is an important addition that most Paxos implementations will need. You will need the ability to bring up a node that goes off for service back into operation and pick up where it left off. Our implementation, of course, has the ability to do this without human intervention. So I'd like to start this section of the presentation with a statement that our chief scientist made. You have to coordinate intent and not the outcome of the change to the deterministic state machine if you want to do active-active. This is a critical difference between approaches that have been traditionally attempted in the Hadoop ecosystem for making standby servers versus what we are building and what we're proposing as the new standard for doing redundant services in Hadoop. So let's take a look at how coordinating intent versus coordinating outcome was. Let's say there are two servers, server 1 and 2. A client connected to server 1 proposes makedir/a. Client connected to server 2 proposes create file/a. In the top half of the slide, I have coordination of intent described, because as soon as this intent is expressed by the client, we send it through the Paxos system, which sequences it. In this particular case, it's create file first and make dir second. So both the servers apply it in the same sequence. Naturally, create file succeeds in both services, make dir fails, so you have consistent state in both of these services. Thereby, you can have active read, write in both services. Suppose we were to take an alternate approach for coordinating the outcome. You have server 1 making a proposal to make dir /a, and server 2 doing create file /a. Both of them apply the change to the state machine immediately. After application, they write it out to the edits log or the HBase wall. You have a problem now. One of these two servers has an inconsistent or wrong state. Assuming you come up with some fancy algorithm to determine which one is right and which one is wrong, you still have the problem of needing to undo things. As you can see, for a file system like HDFS or for HBase, you will not really have a clean solution to this. The result is that you can have at most one active server accepting write or modifications at any time. Every other server has to read from the edits log or read from the outcome of the state change and wait in standby mode. It can be a hot standby, but still, it's a standby. This is the critical difference. If you coordinate intent, you can have active services versus coordinating outcome of change, where you can never have more than one active service. So let me give a brief recap of HDFS. The following slides are courtesy of Konstantin Shvachko, my colleague and dear friend. Many of you may know HDFS already, but these slides provide amazing insight into how HDFS works. If you want to ever learn HDFS in 4 slides, these are the ones. So as we all know, HDFS is a reliable distributed file system for storing very large data sets. The key aspect of HDFS is that metadata is separated from data. Namespace is a hierarchy of files and directories represented by an object called inodes, and attributes such as permissions, quotas are recorded in the inodes. So name node keeps its entire state in RAM. It writes its changes to an edits log, and the written state consists of the most recent checkpoint and a set of journal log edits following the checkpoint. The file data is divided into blocks. 64 megs used to be the default. It's now 128 megabytes. Each block is independently replicated on a set of data nodes. 3 is by default. And block replicas are stored at regular ext3 or ext4 files on local drives on the nodes. So the HDFS cluster in its current form has active standby name node built into the system. The logs are written to either a NAS file system or a shared system like the Quorum Journal Manager. There's a single active name node. All clients connect to that name node. Changes are performed. And then the outcome of these changes are written out to the NAS. The standby sips from that and keeps a warm standby, essentially. There are tens of thousands of HDFS clients and thousands of data nodes. So this is a very interesting slide. How does HDFS operate? It's a great snapshot of how this file system operates. An active name node receives a request from a client. It applies the state to its memory, records the update as a journal transaction, and when the journal transaction has been f-synced, it's on persistent store, the result is sent back to the client. What does the HDFS client normally operate on? It sends requests to the name node. Let's say it's a read operation, gets a list of read locations for the block, and it reads or writes from the blocks directly from the data nodes. It doesn't talk to the name node for actual data operations. The data node mostly does transfers to and from clients and between data nodes. The between data node is for increasing replica count and things like that. It reports replica state change to the name nodes, new replicas found, deleted, corrupted replicas, so that the name node can orchestrate the creation or deletion of replicas. It reports its state to the name nodes using heartbeats and a summary block report. So I want to talk about consensus node. This is our application of a Paxos-based system to create active name nodes. We filed a JIRA HDFS 6469 to make progress in the open source community, and we have a related JIRA, the coordination engine, that's Hadoop 10641, and we're inviting feedback on these, and we're inviting assistance from the community in developing these concepts further. So in a replicated namespace, as I've been talking about in this talk, the consensus node or the C node, all of them play an equal and peer relationship. Clients may connect to any of these. They are load balanced completely, and the clients can ask for modify or write operations on any of these name nodes. Each C node has an exact same copy of the namespace. Namespace changes applied to one are applied in the same sequence to all the other C nodes, so the state in memory and in their independent edits log is exactly consistent. It's a shared nothing architecture, so we don't put the edits log in a NAS or quorum journal or anything of that sort. The coordination engine is responsible for establishing the global order of namespace updates, and in the same order, these updates are applied to the state machine. Here's a pictorial representation of the same clients connecting to any of the consensus nodes. Load balancing happens automatically. Proposals go out for making changes to the state machine, and the coordinated updates are applied to the state machine. Here's how a consensus node workflow normally looks like. This is the orange line is what is different between this and the standard name node operation. It receives requests from a client. It submits a proposal. At this point, no change has been made to the state machine. It submits a proposal to the coordination engine and waits for agreement. The Paxos algorithm is applied, and the agreement comes back in a specific sequence in all of the consensus nodes. The consensus nodes apply the change, and the client is connected to just one of the consensus nodes, obviously. A response is sent back to the client. The other consensus nodes don't do anything with the response. They just record the change and write it out to the edits log. The client and data node operations remain completely unchanged. It's a strict consistency model. This is what results in a fully, strongly consistent exact replica in each of the name nodes, and you can switch, the client can switch from one name node to the other without jobs being interrupted. At any given time, the consensus nodes may be running a little bit further or behind. This is dependent on the state of how fast they're consuming agreements. One way to express this is to consider the agreement sequence as the clock for the system. If they're in the same point in the clock, they're going to be in the same state. But if one is running with a slower hard drive or less memory, it may be running behind a little bit. One copy equivalence is a term that's very familiar to database folks, and by doing a deterministic state machine and applying the same set of changes to those, we have one copy equivalence. There's another piece of code we provide as part of this consensus node system. It's the consensus node proxy. We use the standard Hadoop HDFS proxy provider interface. We substitute the failover proxy provider with the C-node proxy provider. That's the one that knows to switch from one active name node that died to another one and carry on from that. The main feature of the consensus node proxy provider is that it randomly chooses a C node when the client is instantiated, remains sticky to that C node till timeout to one of the requests happens, and it switches to another C node, and it's smart enough to avoid safe mode. There are improvements we could make, and one of those is to make network proximity a factor in the choice of proxy. I'd like to make a brief note of possible alternatives to a Paxos-based replicated state machine and point out the flaws in those. One way to do it, an obvious way, is to use a TCP connection to send the data to 3 of these replicated servers. This is normally called the load balancer option. And the problem with this is that the load balancer becomes a single point of failure. If that load balancer goes down, you have no access to your data. You can't ingest data. Since Paxos is not employed, what you have is that strong consistency cannot be guaranteed, and replicas will quickly diverge. The divergence may be a small fraction, but it'll surely be different. You'll end up with 3 different file system contents. The other option that I've alluded to earlier in my talk is an active standby option where you have the write-ahead log from the HBase or HDFS edits log is written out to a shared storage, and you have a standby server sipping on that, keeping it warm. But as I pointed out, if you coordinate the result of a change to the state machine, you can never have more than 1 active server at any time. So it's always going to be an active standby solution. Here's a little bit of a pictorial depiction of the wall, the HBase wall or edits log being written out by the active to shared storage and then being picked up by the standby and waiting in a warm standby fashion. As I said, only 1 active server is possible. Failover takes time. In the case of HDFS using Quorum Journal Manager, I have a specific comment I'd like to make, which is you're still going to have to go through the consensus mechanism to store it in the QJM. Why not pay that cost ahead of time and have multiple active servers instead of doing it in an active standby mode? So I'd like to finish up this talk with a little bit of insight into how we're building HBase in a continuously available mode. Then I'll hand off to Brett for a demo of our nonstop HDFS running over the wide area network. So the 2 known single points of failure in HBase are the region server and the master. I'm going to talk about how we deal with region server replication using Paxos. What we have is we pick up the client RPC with a multi or a put request, and we push that through the distributed coordination engine. If you use the coordination engine built on top of Zookeeper that's described in Hadoop 10641, you can get the same effect with open source software. So the client calls multi, and nonstop region server intercepts it. It makes the Paxos proposal to our distributed coordination engine, and Paxos is running between these servers. The proposal comes back as an agreement on all the nonstop region servers. Nonstop region servers call their state machine and make their change. The nonstop region server that the client is connected to will send the response back, and that's the end of that put request. It's a shared nothing architecture, so the H files, walls are not shared. There are independent ones of these for each replica of the region server. Replica count in HDFS can be tuned to your requirements. Snapshot of H files, wall tailing, these are all irrelevant in our solution. It's not an eventual consistency model, and it does never serve up stale data. With that, we have a few minutes. Let's take a look at the demo that Brett's going to show of nonstop HDFS. Then we'll open it up for questions.
All right, thank you, Jagain. So what I'm going to do is do a demonstration of a single HDFS running across multiple geographic territories. So keep in mind, this is not 2 different Hadoop clusters. This is a live demonstration running in this particular case, it happens to be running up in the cloud. So I'm running across 2 Amazon regions, EC2 East in Northern Virginia, and also EC2 West in Oregon. But remember, it's a single HDFS cluster. Now, if I take an exposed view inside of the cluster itself, what you'll see is that I have 6 active name nodes. 3 of those name nodes are in North Virginia. Again, 3 of those name nodes are in Oregon. And what's really interesting is this is a synchronous namespace, so whatever I do to one name node occurs on all of them. Remember, as Jagain said, it's a leaderless system, so we're able to actually have client requests hit each one of the name nodes, and any update to the namespace is immediately coordinated amongst its peers. The demonstration that I'm going to do for you today, very simply, is I'm going to run some of the standard sample applications that ship with the Hadoop distribution. In data center 1, what I'll call Northern Virginia, I'm going to run TerraGen and TerraSort. So we'll put some data into HDFS, we'll sort it. And then in the Oregon data center, I'm going to run TerraValidate to prove that all the blocks made their way from the first data center to the second data center. Of course, I don't want it to be easy for the system, so along the way, what I'm going to do is I'm going to fail some of the name nodes. At some point, I'll even bring down the entire network link and show you how we recover from those kinds of failures. So the first thing I'm going to do is I am going to create the files. So I'm going to run this script. And I'm just going to put it in a directory called T1. And again, this runs TerraGen and TerraSort back to back. So one of the first things that you'll notice in the monitoring application, which is basically showing you the RPC bytes in, the green line and the orange line is the RPC bytes out. It's showing you the name node traffic. And one of the things that you've probably seen is that all the name nodes have responded to the event requests. So the upper right-hand window is running in Northern Virginia. It's running TerraGen. So in addition to all the name nodes synchronizing each one of the requests, you're also starting to see these things or these items in the second data center in Oregon called foreign blocks make their way. And what we've done is we've extended basic rack topology, rack 1, rack 2, rack 3, to be data center aware. So now we have data center 1, rack 1, data center 1, rack 2, and so forth. So we can create a write pipeline that allows local ingest to all of the name nodes that are in a single data center, complete that write pipeline, and when each block is complete asynchronously, push the block over the wide area network. And that's what you're seeing here. A complete write pipeline in data center 1, and then asynchronous blocks pushing their way to the Oregon data center. It's an active configuration, which means data can actually travel in both directions. Now, it looks like I've just gone into the TerraSort phase, so let's start to cause some failures. I'm going to drop a couple of nodes here. I'm going to SSH into, let's pick, I don't know, HDP2 and do a reboot. That's the name of the machine here. And let's also cause a second failure. I'm going to SSH into HDP, let's pick, I don't know, 8 and do a reboot. And what I've essentially just done is I have just killed in a row, while running a MapReduce job, while in the middle of TerraSort, I've killed 2 of the 6 active name nodes that I have running in this cluster. But of course, what you'll notice is that the job continues to run without interruption. We continue to replicate blocks for any of those blocks that are still might be outstanding as they cross the network. I've done a TerraGen of about 400 megabytes. Again, all while keeping the system state 100% consistent and allowing the jobs to continue at WAN scope as opposed to LAN scope. So the next thing that you're going to see in the demonstration here is that self-healing part that Jagain talked about. These nodes have been down for some period of time, or at least they have been since the job was running. And there's a global sequence number that we talked about. Each one of them is at the most current sequence it can be at, except for the ones that have been out of sync. And when the machines come back online, they make a little proposal. They say, hi, I just want to let you know that I think the latest proposal is 1,000, and the rest of them say, no, you're considerably behind. We're all at 10,000, and they go into a learning mode. So what happens is when those nodes come back online, they go into safe mode. The client requests are redirected around them while they learn all of the transactions that they missed, and then once they're fully caught up, they become full active participants in the cluster again. So I see those nodes coming back online now. Let's go ahead and take a look at maybe the web UI for one of those. So I'm going to go into HTTP2. I'm going to hit refresh here. And what you should see in just a moment is it says safe mode is on. It's looking for the block replicator. So it's going to take a few minutes. It's going to figure out what the block replicator is. It's going to figure out what the current transaction IDs that it missed are. It's going to figure out a number of things, those items that were behind, and then, of course, catch up. So we'll give that just another moment or so. I'll go ahead and refresh one more time. And then once all of these are caught back up, we'll have a complete and consistent state. Now, given the time we have left, and I want to leave some time for questions, I'm going to do one last thing for you. I'm going to run terravalidate on the directory, the first directory that we created, T1. And I'm going to show you how we're able to keep the namespace completely consistent and that all the blocks replicated from data center 1 over to data center 2. While you kind of watch that in the background, maybe given the time, we can open it up for some questions.
Yep.
And if you do have questions, maybe come up to the microphone in the center so that we can hear you.
Well, thank you for the talk. So I believe Zookeeper has been a distributed coordination engine as well, which using Paxos too. So what is different from Zookeeper with regard to your DCE?
So yes, Zookeeper is a capable distributed coordination engine, and we are building a plugin into our coordination engine API that's Hadoop 10.641 using Zookeeper. Our own engine has more manageability features. It has the capability to run over the wide area network, and it operates in a more scalable fashion. It can process many more concurrent transactions. In the Paxos space, each agreement is a change to the state machine. So our engine can process many of those concurrently, so you can have much higher throughput. Those are the advantages in our system.
You know, one of the other things we see also is that, you know, the ZAB protocol elects a leader. Whenever you have a leader-based system, you have a classic chicken and egg problem whereby, generally speaking, if a leader fails, you can elect a new one, but under various network conditions, like a network partition, you might not be able to re-elect the leader. And if that happens, then of course you can't do failover control.
So in that case, isn't there a new leader required? I mean, you do need to have a leader election, is that right?
So we are a leaderless system. So for each round or each agreement in Paxos, there can be a new proposer. That means that there is no elected leader. So what that implies is that if a node goes down in this quorum, there will be clients that are connected to the other two nodes that make proposals. The state machine will continue to make progress, and the services will continue to be available. The nodes that were connected to the particular name node that went down time out after 14 seconds, which is just a number that we picked, connect to one of the other name nodes and make their requests, and progress continues to be made. There's no leader election in this at all. So for each state change in the deterministic state machine, we have a different proposer. We have the capability to have a different proposer.
I see. And typically, how many nodes are there in your quorum with your engine?
So in the wide area network deployments, we're recommending 3 nodes per data center. If the customers have a particular data center they prefer, one of them turns into the distinguished node. So all ingest in that node happens at local area network speed, because quorum can be accomplished within that particular data center. In the case of a local area network, 3 nodes is perfectly fine. There are some applications that we've seen which have a very high name node load with 100,000 connections or more. Those benefit from the load balancing that we provide. We suggest 5 name nodes for those. That pretty much covers most of our use cases.
So again, a question and a comment. So when a request comes to say make dir or make file, at one name node, you coordinate with the other guys on what the current sequence number is, or whatever you call it, right?
Right.
So on every operation, you need to do a round trip?
That is correct. Every modification to the state machine will require coordination to happen.
Across a majority of the...
Correct. And
so then what would have been interesting here, either on this or another one, is to show what the degradation in services.
It's in performance, you mean?
In performance, yes.
So we've spent considerable amount of time looking at performance. And there are 2 aspects to this. One, reads are load balanced evenly, and they're done without coordination. So we get a huge win from that. Most workloads have an outsized proportion of reads.
Okay.
The second is that the metadata to data distribution is very large. So you do a metadata operation and you write out a 128 megabyte block. So in the overall things like test DFS IO and other such benchmarks, we can't even measure the performance differential.
So would you have run Constantine had written this name node bench, I forget what it's called. So would you have got what's the number for that?
So
that one used to run 6,000 operations on a laptops.
Right. So the NN bench is kind of hard to run because it doesn't use the RPC system, and we trap calls at the RPC system.
Okay. So then there is actually another one called name node load generator. You should try that one, and it'd be good to get those numbers on your Jira.
Sure. Micro benchmarks are useful, and we will publish those numbers.
So 2 comments. One is that you're absolutely right that the current name node 1 is active passive. Okay,
correct.
And it cannot be made active in the ways that you mentioned. It's pretty obvious. But one thing that is incorrect is that it can be made, you can have the other one do read operations. Okay? So
Sure.
for example, the work where you say that most of the work is read. Okay,
Correct.
so from that point of view, The second comment, one comment which I actually have an issue with is that you said that it is active standby failover is error prone. Granted that it'll take longer time. It's currently 30 seconds to 180 seconds. But from an error point of view, it also uses Paxos for its, for its journal, and uses Paxos for its leader election indirectly. So it is as error prone or as non-error prone as your work.
So it depends, right? I mean, Paxos is not just a consensus algorithm. It's a new way to write servers. And when you say Paxos, you really need to look at it as the whole sum. There is a replicated state machine that you apply a set of operations to.
No. I agree, but what I'm saying is, I'm only having an objection to your statement that the active standby is active standby. Nobody's pretending it's active.
Right.
But it is not error prone, is what I'm saying. Okay.
So customer feedback is probably a better use case in this. I don't really want to turn this into an argument. Our customers are happy with this. I think for the whole Hadoop ecosystem, moving to an active environment is beneficial.
I think it's fantastic, the work you guys have done.
Thank you.
And I'll work with you guys on getting this thing, but what you need to do is the other one is not error prone. Okay, so our customers are also happy.
We don't want to offend
They might be
anybody.
happier with this, but the word
Okay,
error prone is not
I will
correct.
take back
It's
that.
technically incorrect because you're now talking about correctness of protocols and everything, and then suddenly you can't take the other one and say it's error prone. If you do, you'll have to show why it is error prone. Is it an algorithm issue or something else?
I think one of the
That's
key
what I'm
things
saying.
that you have to keep in mind is, and this is probably a fair statement, is that the current AJ configuration is a LAN scoped configuration. And what we do is we extend that to WAN scope.
But those are all
But
features. The
we'll
other one
take
is not
back,
error prone.
to go back to your statement, that's a fair point. We'll take back that.
Are you eliminating the QZAMs completely? And because now
Correct.
the name node can do all the consensus, everything?
Correct. It's a shared nothing architecture, and QJM is a shared storage architecture. We don't need the QJM, not with this.
And is your code open source at the moment?
So yes, we filed HDFS 6469 and Hadoop 10641. Design documents are,
What is the first one you said just now?
so we filed two JIRAs, HDFS 6469 and Hadoop 10641. And we're working through the process of contributing this to the open source community with the community. So we invite participation and assistance from you folks.
Is it the fact that you have already demoed? Is this code production ready?
Yes, it is.
All right, thanks.
Two quick questions.
Sure.
How do you deal with network latencies and hardware latencies?
So network latencies are, that's a two-part answer. For the local area network, we have the ability to do consensus in 2.5 round trips, which is not too bad. And as I pointed out to Sanjay, the metadata operations are a small fraction of the total time for a HDFS I/O operation. For the wide area network, we have two capabilities. One is to have this distinguished node in your primary ingest center, and we have the capability to do rotation of that quorum to follow the sun. So there's automated management of these capabilities. With those management features in place, you can do ingestion with coordination at LAN speeds, even across the wide area network.
And what about the hardware? Like
The hardware latency, as it turns out, rolls into just latency. As far as we are concerned, if we send a message out, it goes to the other end, it gets synced to disk and comes back. That's what we consider latency, not just the 10 gigabit versus 1 gigabit latency.
No, when I say that when you're giving the proposal, your number would be lower than the other ones.
Correct.
And so you will get back rejected. And the client.
So we talked about back off. We have sophisticated back off. This is for two proposers contending for the same GSN sequence number. We have sophisticated back off algorithms to make sure that we don't keep stepping on each other all the time.
Yeah, but this one is having a latency, so it will continue having the latency because you cannot see the latest number. So, this person's work would be delayed because it's having a latency. It's not like dead node. So do you kill the node when it has latencies?
You mean the node is running very slow or something?
Yeah.
So if there is a majority aside from this node that's running slow, we're still good because majority will be reached among the other nodes and they'll continue to make progress.
Yeah, but then the work that is, client that is trying to work on this node will continue to have latencies. And
For 14 seconds it waits the way we've configured it, and then it'll reconnect to one of the nodes that's operating normally
Okay.
and makes progress.
So 14 seconds is what the
That's configurable, but 14 seconds has worked out really well for HDFS for us.
Thank you for the talks. And I got a quick question.
Sure.
So you're saying in real world, you recommend 3 name nodes in a Paxos group. So do you have any plots to show or how the cost, like the latency or like the IO per second, how that changes over the, if the group, Paxos group size changed, let's say it's 5 or 7 or 11.
Sure.
So do you have any plots?
We do have benchmarks for the above we can share
So
with you.
just
offline.
for micro benchmark or?
Both micro benchmarks and overall throughput. All I can tell you is overall throughput, it makes very little difference. You can hardly measure because the metadata operation really is a very small part of the overall I/O that's done in HDFS. Micro benchmarks will highlight that a little bit more, so going from 3 name nodes to 5 will have an impact, and we can only use micro benchmarks to measure that. That's
So
correct.
those plots are public or?
We can make those public. We're working towards those. I mean, we're a small company. We're spinning really hard to get these things out. We'll publish them as part of the JIRA.
Okay.
We can.
thank you.
I mean, I can share informal numbers with you ahead of that if you're interested. But Constantine is the master of micro benchmarks, so we're happy to work with you on this.
Okay, thank you.